Good afternoon, everyone. Today we have the pleasure to welcome Professor Jindal Shah. Professor Shah graduated as a chemical engineer in the Indian Institute of Technology, then obtained his master's degree at the University of Cincinnati and PhD at the University of Notre Dame. Professor Shah is currently an associate professor at the Chemical Engineering Department of the Oklahoma State University. Much of his work is devoted to the application of Monte Carlo and molecular dynamics simulation to understand molecular level interactions, phase equilibria, ionic liquids, and dye-sensitized solar cells. He has been also developing an open-source Monte Carlo molecular modeling package, Cassandra, in collaboration with Professor Ed McGinn for predicting thermodynamics and transport properties of complex fluids. He has over 50 publications between international journals and conference papers, which to date have been cited more than 2,000 times. So welcome, Professor Shah. Thank you so much for being here. Please feel free to start your talk.
All right. Okay. All right. Can everyone see this presentation? Good. Okay. Let me start the laser pointer. Okay. Thank you, Yuri, for the kind introduction. And I would like to give my special thanks to Fred for inviting me. Fred and I go way back. We met almost 10 years ago, as I was telling him just a few minutes ago, at a PPD conference in China. And then our conversation led to organizing this Monte Carlo workshop with Professor Ed McGinn at University of Notre Dame. And I had a ball of a time in August of 2011. So it's almost a decade. It's like coming back. So I'm really honored to be here, honored to have this invitation. So as Yuri pointed out, today I will be talking about ideality in ionic liquid mixtures. And then as the talk evolves, you will realize that ionic liquid mixtures are very complex, but we'll get there. So just to orient ourselves, I'm from Oklahoma State University, and when we look at the map of United States, Oklahoma is somewhere in the center of the country, a little bit to the south, just north of Texas, and Stillwater is actually in the northern part of Oklahoma. Very beautiful state. I really love being here. And here is the university, sort of bird's eye view of the university. It's springtime, and there's something that we really have. This is the engineering north. This is actually engineering north. On the fourth floor is the office, is the department, and that's where all of us are housed. This is how my group has evolved over the years. So this is early days of my research group, and as you can see, a number of graduate students and number of undergraduate students have gone through our lab. We have fun times working together. Unfortunately, because of the pandemic, we have not been able to meet in person, but we are really looking forward to coming back, and then having person-to-person interaction. The reason I'm showing these pictures is that the work that I'm going to be showing would not have been possible without this talented group of students that I've had privilege to work with throughout last 7 years at Oklahoma State University. I would also like to acknowledge funding and various computational resources that I have used, or my research group normally uses. So we have funding from National Science Foundation. Oklahoma State University provided startup seed funding to jumpstart my research. And we are very fortunate to have a high performance computing resource at Oklahoma State University. When I started, we had a supercomputing resource, which was called Cowboy. And then we were able to get a National Science Foundation grant to install another cluster, Pete, which is Oklahoma State University's mascot, Pistol Pete. So we have a Pete cluster at our disposal. So we are really fortunate to have these computational resources available at Oklahoma State University. As Yuri pointed out, I have been very fortunate to have worked with Ed McGinn throughout last 2 decades, and we have been developing this open source Monte Carlo molecular modeling package, Cassandra. And this is something that we used in the Monte Carlo workshop 10 years ago. It's in full development. A lot of talented people are working with Ed. And we use Cassandra for calculating gas solubility in ionic liquids. Other resources that we heavily rely upon are, VMD for visualization, Travis for analyzing molecular dynamics trajectories, or Monte Carlo molecular simulations in general. And we also do a lot of electronic structure calculations, for which we use Gaussian, and GROMAX is our molecular dynamics engine. So this actually gives you sort of resources that we use, and then we'll have opportunity to look at some of the results that have been produced by these software packages and my students. So what is the overarching goal of our research? Yuri kind of alluded to the broad themes that we have. But as a molecular simulation research group, our primary goal is in the design of rational materials. And to design rational materials, we make use of molecular simulations. So we do calculations at atomistic level and a little bit coarse grain, a united atom simulations. We also make use of quantum calculations. We are doing electronic structure calculations, so gas phase calculations, calculating thermodynamics and reaction energy barriers. And in the near future, we'll also be looking at QMMM calculations, so where we can couple important regions where reactions occur with molecular mechanics. And I'll allude to in the next slide. Recently, we have also started using machine learning. As I'll explain, ionic liquids provide a tremendous chemical space, and just focusing on molecular simulations or quantum calculations is kind of challenging to navigate the entire space. So machine learning is becoming more and more of a technique that we use. And when we apply these different methodologies, our goal is to predict thermophysical properties of whatever systems that we are interested in, primarily ionic liquids, and specifically ionic liquid mixtures. We want to be able to compute phase equilibria. Our focus here is on gas solubilities. We also looked at water solubilities in ionic liquids. And we also want to calculate electronic structure properties, so that we can think about how ionic liquids can be biodegraded. And all these properties are linked with the structural information that we derive from these calculations or these simulations. And we want to use the structure property relationship as a feedback mechanism to design rational materials. So here is a sort of a brief overview of the type of ionic liquids research that we engage. So I've really highlighted three main topics here. This is the topic that I'll be discussing today, where we are looking at binary ionic liquid mixtures. So this is the cation of the ionic liquid mixture. This 1-butyl 3-methyl imidazolium, which I'll exclusively focus throughout the talk. And let's say you have two anions, this being chloride and this methyl sulfate. We want to see how mixing these two ionic liquids result in various molecular level arrangements of these ions in the system. So here, we are looking at how anion chloride distributes itself around the cation. Same thing with methyl sulfate. And then we'll look at what are the ramifications of these molecular level structures on various properties. One being solubility of CO2. And I'll also talk about sulfur dioxide and ammonia solubility in ionic liquids as a function of these concentrations, and relate that back to the structure, the guiding principle in our research group. We also have effort in looking at how we can change the structure of ionic moieties. For example, if we have the cation, so the imidazolium core is the same as that I showed you here. But now in this case, we are actually going to change the alkyl chain length on the imidazolium cation. It goes all the way from ethyl to dodecyl. And we want to ask ourselves questions as to what would this lead to in terms of molecular level structures that you get in ionic liquid systems. So here we are pairing this with octyl sulfate, which also has non-polar region in the form of octyl chain length. So what we see here is that this is the C2-MIM, or the ethyl analog of the imidazolium cation, all the way to dodecyl. And as we change the alkyl chain length, what we see is that there are these domains that form. So here, all the alkyl chains coming from octyl sulfate, indicated in blue, they seem to have aggregated. But as you increase the alkyl chain length on the cation, different structures emerge. And one particular structure that, like, we are really excited about is the structure when is formed when the alkyl chain length on the cation matches with that of the anion. So here we have octyl imidazolium and this octyl sulfate, and we get this alternating layer. So the green layer is the nonpolar layer, and then red is the polar region. So now you see polar, non-polar sort of segregation. And these type of structures are very exciting for, let's say, energy storage or battery applications. You can think about using these channels as sort of super highways for conduction of ions such as lithium, potassium, like, pick your favorite battery or pick your favorite ion for battery applications. So rather than having a three-dimensional diffusion, one can think about two-dimensional diffusion and increase the diffusion coefficients or transport in these systems. This last uh, research project that we have, or like the third research project that we have, is now looking at ionic liquid biodegradation. Ionic liquids have been studied a lot, and now number of applications in industry are emerging. In fact, Chevron has an application. Petronas in Malaysia has an application based on ionic liquids. So as I'll tell you later, ionic liquids are non-volatile solvents. So like, we can think of eliminating air pollution, but they do have solubility in water, and many of these ionic liquids can be toxic to aquatic organisms. So if there's an effluent discharge, we would like to make sure that these ionic liquids are biodegraded before the wastewater is released in the environment. So here we are looking at how ionic liquids can be biodegraded with this porphyrin systems that we find in cytochrome P450. So we want to understand the thermodynamics and kinetics of these processes, and why some ionic liquids are biodegraded while the others are not. And the last topic that we have is machine learning of ionic liquids. So there are a large number of ionic liquids that one can synthesize. So how do you efficiently navigate the space for the property that that one may be interested in? Here I'm showing ionic conductivity. So there's a typo, but you have ionic conductivity, and this is the data that we have collected at 298K from the NIST IL thermo database. So as you can see, this particular graph is pretty sparse. But what we are able to do is we have developed a machine learning model based on artificial neural network, and all the cations and anions that form these ionic liquids in this set, we have combined them. So like, we have about 30 cations and 40 anions. So you combine them, and suddenly the space becomes 1200 ionic liquids. And we are able to predict the ionic conductivity for those ionic liquids. And one interesting thing that we find is that this combination leads to ionic liquid, which has a conductivity higher than the highest conductivity in the database. So like, this may provide a viable pathway for predicting, or like, designing ionic liquids um, with, with property in mind. We can extend this concept further. Now we can think about forming ionic liquid mixtures. So here we have formed binary C ionic liquids, meaning that the anion is identical, but you have a mixture of cations. And I'm just showing ionic liquids which show non-ideality in ionic conductivity. So Here, we have been able to push ionic conductivity even further. So like, there's an increase in ionic conductivity by forming these binary mixtures. And then you can, extend this to binary anions and reciprocal mixtures. So we think that like, binary and reciprocal mixtures are really a great way to tune the properties of ionic liquids and then, discover ionic liquids of interest. So I'll give you, I talked a lot about ionic liquid research, but I'll give you a little bit of introduction. And it was great that Ed gave a talk only last week. So if, some of you or many of you were there, you know about ionic liquids. Um, as the name implies, ionic liquids are cations and are totally composed of ions. You have cations and anions. So these are non-aqueous solvents, which are made up of cations and anions. So let's think about forming an ionic liquid. Why they are called ionic liquid? We can think about table salt, sodium chloride, which is at room temperature, is a solid form. The melting point is pretty high, all the way up to 800 degrees Celsius. However, a simple substitution of the cation sodium with this imidazolium cation, one of which I showed you earlier. So you have this imidazolium ring, ethyl methyl imidazolium. So by introducing asymmetry and delocalizing the positive charge on the cation, we are able to bring down the melting point by an order of magnitude. So there's a tremendous decrease in the melting point, and this would be classified as an ionic liquid. Uh, so like these are solvents that have a melting point below 100 degrees Celsius. Now we can extend this even further. Let's delocalize the charge on chloride and then introduce molecular asymmetry. So if we have this NTF2 anion, so those of you who are working in the battery field, they would recognize this particular anion. We can bring down a melting point even further, almost by 100 degrees Celsius. So these are liquids at room temperature. If room temperature, we say 25 degrees Celsius. So there are, two things, two takeaways from this slide. One is you can have ionic liquids that are liquids at temperatures around room temperature. And the other thing is, by changing the cation, anion, or both, you can tune a property. So this was something I was discussing earlier in terms of ionic conductivity. But the same principle applies here in terms of melting point. So this will allow us to, discover new ionic liquids just by changing the cation and anion. And then, as I'll show you later, we'll do binary ionic liquid mixtures as well. So when we look at a molecular level, how do these ionic liquids, what kind of interactions are prevalent in ionic liquids? The first one being ion pairs. They are positively charged ions, cations, and anions. So the first thing that is operative in this particular system is electrostatic interactions. And they give rise to ion pairs. There are also hydrogen bonded network, which can really percolate throughout the system. There are many ionic liquids systems that actually show this type of behavior, that you can start from one cation and then you can trace the entire system. You can also get ion clusters. And I showed you an example of self-assembly. So as you can see, your length scales can evolve from simple ion pairs all the way to self-assembly, which can be few nanometers. So like, supramolecular versus mesoscale length scales that one can have. What type of interactions? Electrostatic interactions for sure. I also talked about hydrogen bonding interactions. So where do these interactions take place? So these three hydrogen atoms in the imidazolium ring are prime locations for hydrogen bonding interactions. They are acidic in nature, and especially this particular hydrogen has affinity for the anion and through hydrogen bonding interactions. And this is the one that I'll be discussing a lot as we go further. There are also van der Waals interactions when you have significantly larger alkyl chain lengths that can introduce van der Waals interactions. And you can change this to fluorine, and then you can have different types of interactions. Because of the ring, there's a pi-pi interactions as well. So as you can see, you know, from the design point of view, it gives you a lot of flexibility in tuning these interactions. I mean, some of them may not be or cannot be independently tuned, but there's a lever that we can use to tune the interactions in ionic liquids. What are the properties? Why do ionic liquids uh, why are ionic liquids being studied for such a long time? Because they have negligible vapor pressure. Because of the ionic interactions, many of these ionic liquids are have vanishingly low vapor pressure. I still remember days from my PhD days at Notre Dame, where Dr. John Brennicke's group would pull pretty strong vacuum, 10 to the minus 4, 10 to the minus 5 bar, and still in the gravimetric balance, the weight wouldn't change. So many of the ionic liquids that Dr. Brennicke's group looked at had negligible vapor pressure. They are designer solvents. I already alluded to melting point, how we can change melting point, ionic conductivity. So they are truly designer solvents. They have excellent solvation for polar and non-polar species, because you can tune either the polar component of it or non-polar component of it. And that really allows modulation in the phase equilibria for various species. They are good. They have good electrochemical windows. Some of these ionic liquids have 4 or 5 volts of electrochemical window, so they are electrochemically stable, and that's why there's a lot of interest in using ionic liquids in battery application as well as energy storage. And they remain liquid over a range of temperatures and pressures, giving tremendous flexibility in processing. So I'll quickly go over this applications of ionic liquids. The main takeaway from this slide is there are large number of applications, and some of which I'm not even listing here. But the key properties for each of these applications is what we are interested in. So here, for separation, the phase equilibria, for electrolytes, transport properties, and so on and so forth. And that's why, molecular simulations offer really great opportunity to probe into these properties. Why mixtures of ionic liquids? There has been some work in last few years about mixtures of ionic liquids. We can change the cation and anion, but groups have been looking at ionic liquids as mixtures, and there is an ongoing debate whether ionic liquids are simple mixtures or double salts. And by simple mixtures, what we mean is that are they just mixtures of 2 ionic liquids, or in double salt, where you lose the identity of the original ionic liquids. And I'll have something to say about later in the presentation. Binary ionic liquids offer another handle to change the properties. And it's quite interesting how one can tune the properties. So here, there are several properties that I'm showing, starting from dielectric permittivity to excess molar volumes and things like that. As you can see, depending on the property that we are looking at, either you have ideal behavior, or positive deviation from ideality, or a strong negative deviation from ideality. So when I describe, the title of my talk is Ideality in Ionic Liquid Mixtures. And it's not as straightforward to define what an ideal ionic liquid mixture is, at least. From the thermodynamic point of view, we see that excess molar volumes are really small. But when we look at different properties, they show, these ionic liquid mixtures show very unique behavior. This is about diffusion coefficient. We also collaborated with an experimentalist, Joshua Sangoro at University of Tennessee, where they looked at mixing 2 different ionic liquids, C2-MIM-BF4, so imidazolium with alkyl ethyl chain, and C8-MIM octyl chain in the imidazolium group. So when you mix these two ionic liquids, you can get change the long range structure. So like the self assembly that I showed you, and without going too much into detail, the main result was that one can really tune the dielectric constant as a function of the mole fraction of ionic liquids. So these are the two these are dielectric constants at almost pure conditions. But as you can see, as the concentration increases, it goes actually through a maximum. And then when we look at the dielectric constants, roughly twice. So it's 100% increase in the dielectric constant that can be achieved by mixing two ionic liquids. So what is the molecular level mechanism for these particular behavior? And we can tune further water activity. So here we are seeing anions and cations. Just like when you change anion for a given cation, the water activities, and then when you change cations for a given anion, there's something that you get. But now when you form binary mixtures, what you see is that you can actually access this region which was really absent from pure ionic liquids. So once again, it really opens up the property space as well as chemical space for ionic liquids. I'll skip this in the interest of time. So the research question that we want to answer is, do binary ionic liquids form non-ideal mixtures? And if there's a non-ideality in ionic liquids, how can we quantify this non-ideality? And if there's a way to quantify at all? And what are the molecular level factors that lead to this non-ideal behavior if you observe? Our hypothesis was that when we look at the hydrogen bonding ability, so I showed you that hydrogen bonding interactions are very important in ionic liquids. So if there's a significant difference in the hydrogen bonding ability of the anions, then we can expect some non-ideality. And I'll quantify what I mean by significant difference in hydrogen bonding ability a little later. So my first PhD student, Utkarsh Kapoor, who is actually a postdoc at University of Delaware, he decided, let me look at these two systems, or these two ionic liquids, C4-MIM, once again, the cation that I showed you, with methyl sulfate and NTF2. So very prototypical cation with prototypical anions. And then we'll combine these ionic liquids with C4-MIM chloride. So we form mixtures of C4-MIM, methyl sulfate and chloride, C4-MIM and TF2 and chloride. And why did we choose these systems? So if we look at the molar volume and hydrogen bonding ability of these systems, what we see is that chloride and methyl sulfate have fairly close molar volumes, and in terms of hydrogen bonding ability parameter, they're also pretty close. However, when we look at the C4-MIM and TF2, there's a huge difference in molar volume, as well as the hydrogen bonding ability for C4-MIM and TF2 is much smaller in comparison to either chloride or methyl sulfate. So let's first look at the thermodynamic ramifications of these systems. When we look at C4-MIM chloride and this is the NTF2, what we see is that the excess molar volumes, they actually show a slight positive deviation from ideality. If the mixture were ideal, it would be close to zero. And then methyl sulfate has negative deviation from ideality throughout the composition range. Now, though we see that there is some non-ideality, when we look at these magnitudes, so your excess molar volumes are less than 0.5 cc per mole. And when I showed you the molar volumes of individual ionic liquids, they are in hundreds. So on percentage basis, this is not really true indicator of whether there's an ideality or not. For at least from the excess molar point of view, it would seem that they are ideal mixtures, both of them. Dr. Joan Brennicke actually did some experiments for us for this particular system. And then what we see is that the green symbols, they are simulation predictions, and the purple triangles are experiments. So we were quite excited about this result. So though the excess molar volumes were small, we were able to capture the sign correctly. And not only that, we were able to also capture sort of the maximum in the excess molar volume. Uh, Although the mole fractions are slightly shifted, but we were quite excited because, like, those of you do molecular simulation, they know how difficult excess molar volume calculations are, just because of the statistical uncertainty. So the next question is, when we see these type of behavior, what is the molecular level origin? We can look at self-diffusion coefficient. We can come back, but we looked at the cation anion radial distribution function. So here we are looking at chloride as a function. So this methyl sulfate. What we see here is that the radial distribution function between the center of mass of the cation and chloride doesn't really change as a function of mole fraction. You have slight depression in the first radial distribution peak height, but overall, it's pretty independent of the concentration. However, sorry, this NTF2. So there's some drop in the chloride, and then methyl sulfate. It's very similar. So there's chloride methyl sulfate system. Now here C4 methyl sulfate, you also don't really see much change in the radial distribution function. Now let's look at NTF2. C4 chloride shows great variation in the radial distribution function. So the peak height at the lowest concentration is pretty high. And then as you increase the chloride concentration, the peak height decreases. And the same thing happens in NTF2, that with the increase in the chloride concentration, the association between um, cation and the anion seems to weaken. And we'll explain why this is the case through a spatial distribution function. So here, what I'm showing you is the three-dimensional distribution of the anion around the cation. So you have chloride, methyl sulfate, and I've labeled the hydrogen bonding ability of the two anions. So the first thing we see here is that as we go from chloride, pure methyl sulfate, chloride concentration of 0, all the way to pure C4 methyl sulfate. And we don't really see any change in the three-dimensional distribution. So the ions, as if they don't see the presence of the other anion in the system. So in, like, few minutes ago, I alluded to something that this debate whether these ionic liquids are simple mixtures or double salts. So in this particular case, one might argue that these are examples of simple mixtures where there's no concentration dependence at the molecular level, right? However, when we look at the C4 chloride NTF2 system, the picture is very different. Let's look at chloride distribution in C4 chloride NTF2. So this is pure NTF2 with 10% mole fraction of chloride. What we see is that these three hydrogen bonding interactions are immediately occupied, while this particular region is not as developed as the other three. So the first takeaway is that these chloride anions tend to occupy the hydrogen bonding site around the cation, even at the lowest concentration. So these three lobes give rise to the increase in the radial distribution peak height. And as you add more chloride, now this particular position starts populating. So the decrease in the peak height you see is because of the population here. So, like, your chloride is now more uniformly distributed as the concentration increases. Let's look at NTF2. Once again, the NTF2 is pure NTF2. You have strong hydrogen bonding interactions. But as you add chloride, what is happening is that, especially at equimolar concentration, you see thinning of density for NTF2 in the equator region, in the plane of the imidazolium ring. And also, like, the NTF2 here starts depopulating. When you have very high concentration of chloride, as you can see that this site is completely eliminated, while the in-plane site is also eliminated. So the region around which NTF2 occupies, around C4-MIM, starts shrinking. So it's sort of like, dissociating from C4-MIM. So here, this is an example of double salt. So once you have chloride and NTF2, the presence of one anion starts affecting the molecular level organization of the other anion. So, like, based on these two examples, we can see, like, the simple mixture versus double salt. So we cannot really identify whether, like, binary ionic liquids are one or the other. The question is, or the answer is, it depends. And it's not a very satisfying answer. Like, when we say it depends, what would it depend on? So Utkarsh took this study further and looked at how does the molar volume of an ionic liquid vary with the hydrogen bonding parameter. So as you can see, when you have low hydrogen bonding ability anion, your molar volumes tend to be large, and with increase in the hydrogen bonding ability, you have stronger interactions between cation and anion, which tends to bring down the molar volumes. So can we use this and figure out sort of a rule that will allow us to distinguish between simple mixtures versus double salt? So here is the calculation that Utkarsh did, where he actually took the difference between the molar volume. So, like, this different symbols represent different ionic liquid mixtures. So, for example, when we look at this black circle, it is trifluoroacetate combined with chloride. So it's kind of like, a little bit difficult to figure out which is what. But if you have questions, please ask me. But the general idea here is that we are looking at difference in the molar volumes and difference in the hydrogen bonding ability of the constitutive anions. And what Utkarsh saw was that if you are in this region, so, like, in this rectangular region, where the difference in hydrogen bonding ability is less than 0.4, and the molar volume differences are not huge, then you would form native molecular structures. So, like, they are examples of simple mixtures. However, if you are in this region, you will form this non-ideal structures at molecular level. So this provides a very simple and efficient way of sort of distinguishing between ideal ionic liquid mixtures and non-ideal ionic liquid mixtures. So this, like, from a very fundamental point of view, it was very satisfying that we were able to demonstrate that by looking at these differences, one could infer, without even doing molecular simulations, whether these structures are ideal or non-ideal. We always want to answer, as, like, as chemical engineers, we want to answer this question. Okay, so, like, we have this information that ionic liquids can be ideal or non-ideal. But then, so what? Like, is there an application that we can think of? So let's first look at a radial distribution function, which will guide us to where I want to go. So here we are looking at CF3 interaction with this particular hydrogen bonding site. So this is, like, the site that I mentioned. As you increase the chloride concentration, what we see is that this CF3 is once again, quote unquote, becoming detached from H2. So now it has this ability to interact with any other solute in the system, if there is any. So how can we exploit this particular behavior? So here I'm showing a CO2 mole fraction as a function of pressure for a number of ionic liquids. So what are these ionic liquids? So like, they are all fluorine-based ionic liquids. So as you can see, when you have fluorine in the system, the CO2 mole fraction tends to be higher as opposed to non-fluorinated anions. So maybe we can use this idea that CF3 becoming free might allow CF3 to interact with CO2, and that will increase the solubility. So we wanted to calculate what are the CO2 solubilities in these mixtures. We'll quantify that in terms of Henry's constant, and whether the Henry's constant will show non-ideal behavior or non-linear behavior in these systems. And our hypothesis was that the presence of non-native structures, so double salt concept, will translate into higher CO2 solubility, at least for this particular ionic liquid mixture, which has fluorine in it. So what did we do? It's thermodynamics. So let's actually look at the thermodynamics of gas absorption. We calculated Henry's constant, the definition of which is given here, and from molecular simulation point of view, we calculated excess chemical potential in these systems. And most of you know this thermodynamic integration. So we took the CO2 molecule and coupled with the ionic liquid with lambda equal to 0 decoupling, and then lambda equal to 1 fully coupled system, and we measured the excess chemical potential. So when we look at the CO2 Henry's constant as a function of chloride concentration for this system, chloride methyl sulfate. So as a reminder, this was an example of a simple mixture. What we see here is that these two ionic liquids have Henry's constants which are similar. And when we form the mixture, we also see that the Henry's constants are not too terribly different from your ideal predictions. And note that when we compute Henry's constant, the ideal means this harmonic mean of Henry's constant. And that comes because of free energy rather than excess molar volumes or excess enthalpy. Now, when we look at NTF2 based system, chloride and NTF2, what do we see? That NTF2 has lower Henry's constant, so higher CO2 solubility, while chloride has much higher Henry's constant, so low solubility. And then when we do these calculations, what we see is that our calculations are lower than the experiments, but they follow the same trend that from the linear line that there's a slight deviation. So we do see some effect of non-ideality in this mixture. So then we looked at more the molecular level organization of CO2 around the ions. And what we saw that as expected, as the chloride concentration increased, the CF3 interactions with CO2 increased. So our hypothesis was sort of being proven here that there's an increased CO2 interactions with CF3 as the chloride concentration goes up. We also looked at the coordination number of CO2, and that revealed quite a bit of molecular level mechanism of CO2 solvation in these systems. So here we have CO2 interacting with the oxygen, the blue symbols. And as we can see, as a function of chloride concentration, there's some increase, but relatively it's pretty uniform. Same thing with methyl sulfate and chloride. However, when we look at the chloride NTF2 system, what we see is that with the CF3 group, the coordination number increases quite a bit. So you start with 4 and it goes all the way up to 7. And then once again, this is because of the non-native structures that you form where NTF2 is no longer associated with C4-MIM, which allows CF3 to interact with CO2. So as you can see, when you have ideal structures versus non-ideal structures or native versus non-native, it does affect the solvation mechanism of these systems. We also did this spatial distribution plots of CO2 around NTF2 and methyl sulfate, but they actually give you very similar information that CF3 is interacting with CO2 in an enhanced manner with concentration. So we also extended the study to sulfur dioxide. So Regan Black, one of the undergraduate students in my research group, she did this calculations, and in in sulfur dioxide we actually see a slightly different behavior, that the SO2 Henry's constants are slightly higher than what would be predicted on the basis of ideality. We are still investigating what the reasons might be. If you look at the other case, like SO2 and CO2 both are acidic gases, but ammonia being basic, we also see a very similar trend, that there's some deviation from ideal structure that one can expect, or ideal combination law that one can expect for these systems. So um, the molecular level organization of the ions does affect various properties, especially phase equilibria properties. Extending it forward, as I showed you for the machine learning case, that we can also get non-ideality in ionic conductivity. This is a very busy slide, but what I want to impress upon is the fact that when you have these binary ionic liquid mixture where you have common cation and two anions, so this anion combination, one can get very many non-ideal systems where ionic liquid conductivity actually goes through maximum. So this, once again, it's very encouraging that one can get these enhancement in ionic conductivity just by forming mixtures of ionic liquids. We see a very similar behavior if we have ionic liquid mixtures in which cations are the mixture. So C1, C2 are two cations sharing a common anion. And so these are the predictions, and we want to understand molecular level mechanism by which you see this enhancement in conductivity. And combined, there are about 6,000 ionic liquid mixtures that we have discovered. So there'll be too many for us to do molecular simulations on. So if there's an interest, just let me know. We just submitted this to Fluid Phase Equilibria, and there's also Chem Archive, which you can download to get more information about this particular topic. So this, entirely based on machine learning predictions. All right, so in the end, what are the main takeaways from this talk? We talked about two different types of structures. One, I showed you for chloride methyl sulfate system, where increase in the concentration or change in the composition of the anions doesn't affect the molecular level organization, which translates into this fairly ideal system where CO2 Henry's constants can be predicted fairly accurately. And then the other system, chloride NTF2, where the composition does matter because it translates into molecular level arrangements that are quite different from pure ionic liquid systems. And this is where I think the exciting area of research is, because these non-native structures can be exploited for various property tuning. And one I've showed you CO2 Henry's constant, and I've also shown you ionic conductivity enhancement. So at this point, I would like to close this talk. Once again, thank you very much for your attention. Fred, thank you once again for this kind invitation. And I hope to generate some questions. If not, email me later on if there's something that shows up or you think about. Thank you very much.
Thank you so much, Professor Shah. We are now open for questions. If you want to ask one, please feel free to enable your microphone. And you can also write questions on the chat. Our YouTube viewers can also feel free to write questions on the chat. So who wants to be the first?
Eu queria.
Of course, go ahead.
Professor Shah, thank you very much for your presentation. I was just wondering about your final observation, say a bottom line observation about combination of two ionic liquids to enhance CO2 solubility. I was not sure if I could perceive what kind of enhancement we would get when we observe what common single ionic liquids can perform with CO2. But would you expect also an effect of pressure if, in fact, a non-ideal mixture would enhance CO2 solubility?
Yeah, that's a very good question, and I've not shown you any data, like, apart from about what I presented in this talk, to suggest that, like, the binary mixtures would lead to enhancement in CO2 solubility. So this is at this point is conjecture that, like, it will enhance because what we see here is that the non-native structures do have effect on solubility, or, like, this ionic conductivity that we see. And then we have probed probably, like, a tiny fraction of, like, billions of ionic liquids that one can envision, and like, binary ionic liquid mixtures that one can envision. So it's very too early to say whether, like, this will enhance CO2 solubility. But one thing that I didn't show in this particular talk is the CO2 methane solubility, the mixture calculations, where we do see that the selectivity of CO2 versus methane can be manipulated and enhanced versus pure ionic liquid uh, selectivities. So may not like, CO2 as such, the solubility may not be enhanced to the extent that you want, but when we talk about mixture solubility, the selectivity could be affected, because now your CO2, even if there's slight increase in CO2 solubility, your methane solubility could go down, and that can increase the selectivity. So separation wise, that's where I think, but I don't really have the data to back it up, as in, like, extensive data. So there's just, like, one example. Yeah.
Okay, thank you very much.
Ryan the Fever wrote something on the chat. I don't know if he wants to speak or.
Yeah, I can speak. So yeah, so my question, very nice talk, first of all, thank you, was for the Henrik's constant calculations, did you do that in Monte Carlo or molecular dynamics? And then related to that, did you have any difficulty converging those calculations? Mainly in my experience, due to what I presume in your case also would be the sluggish dynamics of the ionic liquid.
Definitely. Like, we do see that, like, the convergence can be an issue. So, like, we run these calculations pretty for a long time, as in, like, and to answer your first question, we use molecular dynamics to do this. So, like, we use GROMACS engine to calculate excess chemical potential. And then when we do excess chemical potential calculations, we have to have um, I don't know, anywhere between 40 to 60 lambda points. So, like, these are really expensive calculations.
Okay, yeah.
So, like, so convergence is an issue. We run this for, like, 20, 30 nanoseconds to ensure that the system is really equilibrated. Yeah, so these are not easy calculations. And that's why I think, like, doing molecular simulation for binary mixtures, just because of the explosion in the combinatorics, is next to impossible. Because these do take time. So I appreciate, and that's why we are looking at, machine learning techniques as, like, very many other people. So I think a combination of molecular simulation and machine learning is where I think probably the field is going.
Yeah.
But I could
Thank
be
you.
wrong.
Raul Fuentes, you can go ahead and ask.
Hi, Professor Shah. In our
Oh,
research,
can you open your camera, please?
I need to change to my
No problem. No
phone.
problem. Go ahead. Sorry.
Sorry.
Let me stop the share. Yeah, go ahead. Yeah.
Professor Sam, we are in our research. So when the chargers are changed in order to describe better the experimental data. We
Mhm.
talking about the ions. We can describe better the interaction with water and the interaction the ions. Uh, my question is about the force fields that you use for this for your research. What kind of force fields do you use? What think about that?
Yeah, great question. In the field of ionic liquids, force field can be, a big challenge, right? Because when we started the ionic liquid field, we were using +1, -1, and then Ed McGee's group has shown, amongst very many, that scaling the charges really improves transport properties and very many other properties. So for this particular application, or the simulations that I showed, or the calculations that I showed, we used united atom force field, at least for the first part where I was showing chloride NTF2 and chloride methyl sulfate. And the charges were plus minus 0.8. And when I showed you sort of extension where we were looking at difference in molar volume and difference in hydrogen bonding ability, those were +1, -1 charges with all atom force field. So what we observed that when we want to compute molecular structures, at least the structures that we calculated, they are pretty much insensitive to the scaling or the type of model that you use, all atom versus united atom model. So that is one thing. Water ionic liquid force field, that's pretty challenging. So when I was with Ed, we published a paper with a student where we looked at water solubility in three different ionic liquids, going from very hydrophobic to hydrophilic. And then it seemed that depending on the type of ionic liquid, the scaling could go from 0.8, 0.9 to 1. And recently, we've also done some calculations for C2MIM and various acetate-based anions, and we are calculating the activity coefficient of water, where you have to change the charges. And once again, 0.8, 0.7 to 0.8 seems to be a magic number where you get even water activity coefficients in line with experiments. And we can talk about what errors we are talking about when we say in line with agreement. Our calculations or our experience suggests that we can get activity coefficients within 1 log unit, natural log unit. So within a factor of 2 to 3. But once again, if you want to get very accurate activity coefficients, I think there's a lot more work that needs to be done. The other thing is, one thing that I didn't really address, and it's not been addressed in the literature as well, is when you have two anions or two cations, we are using fixed charge as we go from, let's say, C4-MIM chloride all the way to C4-MIM NTF2. But the presence of chloride will affect, NTF2. So I've seen only one paper where the change in the charge as a function of concentration has been discussed. And in fact, there are some XPS experiments that suggest that the electronic binding energies are affected when you change the concentration. So it means that from the molecular simulation point of view, we need to take into account those interactions. So ab initio molecular dynamics is one way to go, and we have some effort in that as well. The other thing from application point of view, it opens up opportunities, because if you can change the binding energy of electrons just by changing the composition, it can open up ways in which you can do reactions which might not be possible in pure ionic liquids. So those are some of the ideas that might be worth looking into. But it's a great question. Technical details do matter, and there's a lot more work that needs to be done.
Thank you very much.
Professor Niels Hansen wrote some questions on the chat. Feel free to ask.
Yeah, thank you. It's more a small detail, but you showed radial distribution functions, I think, for various concentrations. And if I remember correctly, the peak height starts to increase if the Cl minus concentration went down. Could this be also an effect just of the decreasing concentration of Cl in the system, and not only about the increased ordering?
Let me share the screen.
I think it was somewhere at the beginning of the talk.
Right. So let's see. Yeah, we are talking about this, right?
Yes, exactly.
Okay. So if I understood the question correctly, so what happens is this orange is actually low chloride concentration. So like this 1090 that you see. So as you increase the chloride concentration in the Cl NTF2 system, the first peak height actually drops considerably from 6 all the way to 3, right? So here there's some drop, but it's not that perceptible. So the way we think about this is in this scenario. So this is a very nice, I like this because it really explains what's going on in the system. So at very low concentration of chloride, because chloride has a stronger hydrogen bonding ability than NTF2, it populates all the 3 sites here. So your strong localization is around this hydrogen atoms. And as you add more and more chloride, what is happening is that this site, which is connected to the methyl position, it starts getting populated. So this is what we see is that the decrease in the radial distribution peak height that you see is because chloride concentration is now becoming more uniform. So if you think about radial distribution function as an indicator of localization, as you increase the chloride concentration, that localization is not as pronounced as one would see at lower chloride concentration. If that makes sense, right? So sorry, I forget the follow-up question on that based on RDF.
No, I just was wondering because the RDF is normalized by the average chloride concentration, and once you decrease it, the peak might go down without any enhanced. No, the peak might go up without any enhanced ordering, basically. So it might make sense to look at the absolute, like the local densities of chloride, maybe.
Yeah. And when we did this, my student and I went sort of back and forth as to is it just the artifact of lower concentration of chloride? Because now instead of 0.9, we are dividing by 0.1, right? So are you artificially inflating that size? But if that were the case, I would see a similar enhancement in the chloride methyl sulfate case as well. Right, at the same concentration at 0.1. The other thing that we have done is we have looked at the coordination number, which I didn't show. So the coordination number seems to indicate that you have a linear trend as a function of mole fraction. So at lower concentration, whatever the number is, 1 chloride, it goes all the way to 4 or 5 for pure ionic liquid systems. So you do see that number of chloride ions in the first solvation shell is less at lower concentration. So yeah, I'm exactly not sure. I'm hesitant to say that that's the cause of increase in the peak height. And I think that's why you want to express that as a function, as radial distribution function, because if you do local density, then the local density will depend on the mole fraction. Here we are normalizing with the bulk density, but I understand your point, and I may have to think a little bit deeper into that. So thanks for pointing that out.
Okay, thanks a lot.
Professor Silvana Materi wants to ask a question.
Okay, my video is always very bad. I don't know why it distorts.
It's good. It's good. Thank you.
Hi, Jindal. Very good
Silvana.
talk. Very good talk. I was wondering two things. First, have you thought about calculate also the viscosity, obviously with molecular dynamics, not simulation, and compare with the not only you did the self-diffusion. Yes, I thought about comparing the ionicity of the ionic liquid, not only the density, or not only the conductivity, but the ionicity. That is very interesting, and also these alpha and beta that you calculate that are can be related. You tested again against the solvatochromic probes, because you have experimental data on solvatochromic probes and how it is correlated.
Yeah, so excellent question. We would like the experimental community to make a lot of measurements. I mean, starting from thermodynamic quantities all the way to probing the solvation structure, because we are doing a lot of these calculations, and as I showed you for the ionic conductivity, we see this nonlinear behavior. It's exciting, but at the same time, these are predictions, and these are based on these machine learning models. So if there's an independent verification from experimental side, that would be really encouraging. Coming back to your question about ionicity, I think in this paper we did calculate the ionicity, and we looked at what is that? We calculated ionicity indirectly, in the sense that we looked at the self-diffusion coefficient from Nernst-Einstein equation, and how the ratio of Nernst-Einstein versus Einstein. I always get confused. So one or the other. But and I think I'm pushing my memory now. They remain flat, but we do have that information. So I can send you that information definitely. Okay. And then if you have the ability to do solvatochromatic probe experiments, I'll be more than happy to collaborate. Yeah.
Okay.
But we do have those calculations done. It's just that I don't remember right now. Yeah.
Okay. Thank you.
Does anyone want to have a question? Okay. Go ahead, Professor Fred.
Hi, Jindal. Let I ask you, I have two questions. One is, you start to show us in slide 2 the bilayer structures. And I wonder about the size of the bilayer.
Yeah. Okay. So what Fred is referring to is this particular slide that I showed early in the talk. It's going to take some time, but we'll get there. Yeah. So when we are looking at this bilayer structure, so what we have found is the following: that these domains that you see, the alternating polar and non-polar domains, they are about 3 nanometers, 3 to 3.5 nanometers in length. So you have polar, non-polar domains that are separated by these length scales.
It's nanometer, you say, or angstrom? Nanometer, yeah?
Yeah, 3 to 4 nanometers, so about like 35 angstrom.
That's nice.
Yeah, so like that's the separation that you see, or the length scales that you see, and this is very evident. It's not the same system, but when I showed, yeah, so when you look at this particular scattering function, here we have this C8 mem, which is the octyl part that I talked about. Here the anion doesn't have the alkyl chain length. So the peaks that you see are indicative of this polar non-polar transition, and it's this Q of 0.25. It's 2 pi divided by 0.25. So you'll get like roughly 30 angstrom of separation. Interestingly, what happens is, oops, what happened? Interestingly, when we go to higher length scales, or not higher length scales, but higher alkyl chain length, so C8, you have 35, 40 angstrom. But as the mismatch between the octyl chain length on the anion and the cation increases, that actually drops. So like you start getting this interdigitation, which reduces the length scale. Yeah, so you also see a non-linear behavior in this length scales. These are not mixtures, but once again, playing with the cation anion identity. Yeah, so they are very interesting systems.
Another question is about, you start to talk about what the difference between two salt system and mixtures. So it's not clear to me what the difference about this.
Yeah, so the difference. So what Fred is talking about is this particular. Right. So the question is posed like mixing ionic liquids. Are they simple mixtures or double salts? And the way in this paper simple mixtures are defined is that individual ions, they retain their identity. So basically, like if you mix ethanol and water, like ethanol and water is still like has its pure properties. In double salts, you cannot distinguish where that particular mixture must have come from. So what we are suggesting, and I'm open to interpretation, is when I look at this particular arrangement of anions around the cation, let's look at C4-Mim chloride and how chloride distributes itself around the cation at when it's in pure form is pretty much indistinguishable from very low concentration structures that form, right? So it seems that the identity of C4-Mim chloride or chloride is not affected at the molecular level by the presence of methyl sulfide. And the same thing I observed for methyl sulfide. This is pure methyl sulfate. And then even at the highest chloride concentration, the local arrangement is pretty much the same, right? When we go to, so this would be an example of a simple mixture, right? But here, the identity of the anions start affecting the presence of the other anion. So here, chloride is not really affected as much, but still you see that at very low chloride concentration, this site is hardly populated as opposed to the pure ionic liquid. But the dramatic change in the local organization is for the lower hydrogen bonding anion, where the anion actually starts separating from the central cation, which you don't really see in pure C4-Mim and TF2. So this is what we would say like it's a double salt. That like the systems are very different, and they are different at various mole fractions. So you can treat each of these mole fractions as kind of a unique ionic liquid in itself, at least from the molecular point of view.
as if one example is the kind of binding so strong that you treat different when the other one is not so strong, the binding effect. Is it?
Right, right. Yeah, so like, that's exactly, and I think like you described much better than I did, that this chloride is, strongly binding, it's strongly hydrogen bonding with the central cation. But because now the interaction of chloride and C4-MIM is stronger, that like, your chloride is displacing the NTF2 anion from its favorable positions. Yeah.
Thanks.
Do we have another question? Since there's no more
I
questions.
have one small.
Okay.
How long is your calculation about dielectric constant? You show some calculation.
Okay.
For dielectric constant. For non-charged molecules, it's not that difficult to do, but for ionic liquids, it may take long to converge. I don't know.
Yeah. So, thanks for that question. And I should provide a clarification. So the data that I'm showing about the dielectric constant, they are experimental data. And then we did, So and then we did molecular simulations to explain the change in the structures that would sort of correlate with the increase in the dielectric constant. So your system goes from globular more to filament-like, and that changes the dielectric constant. So yeah, so we didn't do the dielectric constant calculations, no. But you are right. For ionic liquids, it would be pretty challenging. I'm not saying it's impossible. And I think Christian Schroeder's group, they have done some calculations on dielectric constants, and they run for hundreds of nanoseconds these systems to get dielectric constants.
Yeah, that I respect.
Yeah.
Thank you.
Do we have another question? So since there's no more questions, I want to thank you again, Professor Chang, for the presentation, and I want to thank everyone for the discussion. And now we're headed to the final announcements.